Okay. So this artificial neural network is a very commonly used supervised classifier, right? I'm sure you have heard of it. Okay, the more recent reincarnation of this method is known as the deep learning. Okay, basically deep learning is sort of like a kind of larger model where inside there they have got it consists of multiple artificial neural networks, okay, of different kinds of layers, right? So, so your deep learning is basically built on artificial neural network modules, yeah. So let's look at what this thing is, yeah, ANN. Okay, so basically we first talk about the architecture, right, of this model, of the ANN model. And this model uses a graph, right? This is the graph in the context of networks, yeah. Okay, not in the context of analysis, right? So basically you have the following. For example, if your data set has three variables, yeah. So this will be x1, x2, x3. Okay, so this is what we call the input layer. All right. So this is where you get your data. All right. And then after that, you have what is called a hidden layer. Okay. So this hidden layer consists of a set of nodes. All right. And you can specify how many nodes you want to include. Okay. So let's say if you have two nodes. So this one I will denote it as Z1 and Z2. Okay. So these are the nodes in the hidden layer. And in general, you can have multiple hidden layers. Okay, many. We will just talk about the simple case of one hidden layer. Right. Generally, when you have more hidden layers, your artificial neural network will fit better, right? But it may also overfit the data, right? So one way to actually improve your ANN is actually to add layers and also tune the number of nodes in the layer. Okay. So now then, once you have these nodes, right, then there are connections between them. Okay, so you will have so we'll have, let's say, a connection between okay, that goes from these three input nodes, right, to node Z1. Okay, so these are actually directed edges. So these are what we call edges, right? This is an edge, and these are directed. So the flow is in one direction, okay? And then similarly, you can have you can also have a connection from x1 to like this, okay? So this is what we call a fully connected graph, right? So every node is connected to one another, okay, in this case. So it's so you can see that this node is connected to all the other three nodes, right? Okay. So basically you have this, okay? And then if we are dealing with the case of binary classification, we can actually have another node here. Right. Whereby you can have you can again have an edge, right, from the hidden layer. Okay, the nodes in the hidden layer, then they go to the final node here, right? So this is the last layer of nodes. Okay, so this one you can have it like, let's say y1. All right, and so generally there is also another node here. You can have y2. So binary, you basically have two classes, right? So then you have another connection from here to here. Okay. And then finally, here you have the output. Okay. So this is so this is the output nodes. This is the output layer. Okay. So this will indicate 0 or 1. Yeah. Okay. So finally, it will decide whether it will classify as 0 or 1. Okay. Of course, if this is classified as 1, this will be 0. Okay. It can't. There's only one. So if one of the node has already taken the value of 1, then the rest will take 0. Yeah, in the output layer. Right. Now, so this is the architecture of a neural network. Okay. And the important parameters in this model are the following. So you have the edge. So here's an edge. The edge has a weight, right? So we will denote this as, let's say, alpha. This will be alpha 1. Okay, 1, 1. This one I'll call it alpha 1, 2. This one I'll call it alpha 1, 3. Okay. So the 1 here denotes the this node in the hidden layer, right? This is a node 1 in the hidden layer, and the second number indicates the source. Yeah, it comes from the x1 node. This one comes from x2 node, and this edge comes from x3 node. Okay, and similarly over here you will have your other parameters. So this will be alpha. I will put this as 2, 1. Then you have alpha 2, 2, and this will be alpha 2, 3. 2, 1. Okay, okay. So this is actually 3, yeah. Right. Okay. So these are the parameters. Actually, there's also an intercept parameter. So I'm just going to draw it out here. So to represent the intercept parameter, there is actually another node here. Okay, so this will indicate the this is sometimes called a bias. Okay, this is actually your intercept parameter. Okay, so basically this will be a 2 naught, and this will be a 1 naught. Right. Okay, so basically this just introduces the intercept parameters, but I put it here to relate it to the architecture of the neural network. Right? So for this layer, you have the alphas. For this layer, you have the betas, right? So here you have, let's say, here you have beta 1, 1. This will be beta 1, 2, all right? And this will be beta 2, 1. This will be beta 2, 2, all right? So as usual, you will have a bias, okay, over here. Okay, which is basically the intercept parameter. So this will be beta 1, 0. This will be beta 2, 0. Okay. All right. So these are the parameters of your ANN model. Now, at the first layer, so let's look at how these values are actually used. Right. Okay. Suppose we know. So let's say, suppose we know the optimal parameter values, right? Actually, these parameter values have to be estimated from the data, right? But let's suppose we know them, right? So that things are easy to discuss in terms of the theory. Then you would have the following, yeah? So the value of Z1 is equal to, it's actually determined by a linear function, right? So you basically have alpha 1, 0, okay, which is this contribution. Then you plus the contribution from x1 with weight alpha 1, 1. And then you plus the contribution from x2 with weight x alpha 1, 2, x2. And then you add the contribution from x3, yeah, so with weight alpha 1, 3, okay? All right. So then the value of Z2, okay, not yet actually. Actually, not exactly equal to, but it's equal to, Z1 is equal to the following. So this is the input, a linear input to the function here. This is a function which we call the activation function. Okay, we'll look at that in a while. Okay, but let's continue. So Z2, again, we have an activation function with the input, linear input given by alpha 2, 0 plus alpha 2, 1, x1 plus alpha 2, 2, x2 plus alpha 2, 3, x3. Okay. Generally, this is very cumbersome to write out like this. So usually we will use the linear algebra notation, right? So basically, this is just you can write it like this: alpha 2, and then this will be x. This will be a transpose. Okay. This is the x vector. Right. So this is basically 1 times 3. This is 3 times 1. Okay. So usually you want to write a more concise form, you write it like this. Okay. Alpha 1 transpose x. Okay. Right. So the activation function, right? So okay, so you know now that the value of Z1 and Z2 at these two nodes, they are determined by the linear input, right? But then there's a kind of a function that actually maps this values, right, to another value, okay? So we're going to talk about some activation functions. There are several possibilities. The most common one is something called the sigmoid function. Okay, so the sigmoid function looks like this. Okay, let's say this is W. So this will be equal to 1 over 1 plus E of minus W. Okay, so a sigmoid function, when you graph it, it looks like looks like this, right? Okay, you can see that as your W increases, right? So basically this will converge to 1, yeah? It will converge to 1. And if your W is going to negative infinity, then basically this will converge to 0, right? So the curve looks like this, okay? Of course, you can basically, if you don't know how to sketch this, you can use R to find out, yeah? You can just plot this function. And then, so this is the classic one, and there are a few more that are more popular now, okay? So the popular ones are, there's one called the ReLU. ReLU, okay, is a short form for something called rectified. I think something called rectified linear unit, okay? Basically, your ReLU function is equal to, it's basically a simple function. It's a piecewise function, max of 0 and W, okay? So basically, when you graph it, your ReLU will look like this. So your W, right? Okay. So your W is basically a curve like this, isn't it? Right? It's a straight line, okay? But you're taking the max of 0 and W, right? So on the side where your W is actually negative, okay? On this side, your W is negative, right? Okay? So you have negative value. So the max of 0 and the negative value is actually 0. So that's why your ReLU over here, you don't have this part, but the moment it goes to negative, it becomes 0 flat. And then after that, it's linear like this, okay? So this is called a ReLU. And then there is another one that is called, let me clear some space here. I'll just clear, okay, maybe I'll just erase, make some space so that I keep this part. Then there's another one called the soft plus. Okay, the soft plus is a function like this, log of 1 plus E of. Okay, 1 plus E of W. With log, okay. This one, if you graph it, let's see how it looks like. Okay, so this will just keep on increasing. So your log function is so basically keeps on increasing like this. Right. A slow increase because it's in log scale, yeah. As your W becomes larger and larger, yeah. So basically, it's so when EW is large, then your 1 plus E of power W is basically E of power W. So log of this will basically be W, right? So basically, this soft plus is actually quite close to your rel U, yeah. Okay, it's a kind of like a similar kind of behavior, except that it doesn't become exactly 0, right? It's there's still a bit of a tail value here, some residual values here. Okay, soft plus, rel U, the more modern ones. The sigmoid is very old already. Okay, and then there's another one that's called swish. Okay, a funny name. Swish. Okay, the swish function is given by basically x time x. It's basically a simple modification of your sigmoid function, right? So you just multiply with w, okay? Then you get something called a swish function. This is so this swish activation function is a kind of new activation function that is proposed by the scientists in Google when they use neural network to do their machine learning work. All right, so they wanted to, they kind of like for their work, they found that the activation function that are used in standard work do not suit their problem well. So they kind of like created a kind of it's basically a hack, right? But it's a kind of a clever hack because it basically is a kind of modification of the sigmoid. The swish basically looks something like this. So your W can go to, it can actually become negative, right? So it can go to negative. So once you have negative, right? So you will actually become negative, but then it will actually go up again, go up like this. Okay. So it actually can become negative when your W is on the negative side, right? Okay. So it's also kind of like similar to your rel U and possibly the soft plus. They are actually not too different. There are some differences, but not too different. Okay. All right. So these are the activation functions. And what happens is that it basically, like for example, over here, you have these values, right, as the input. Then basically you just like for example, if you use the switch activation function, what happens is that the value of Z2 will be, you take this linear value and you plug it in here, okay, to compute the value for Z2 and Z1, right? This is what is meant by the activation function. Okay, so from the activation function, you obtain the value for Z1 and also Z2. All right. And after that, basically, then you want to compute a value for Y1. Okay. So the value for Y1 again is obtained from your activation function. Yeah. Okay. So well, okay. So over here, I think you may choose to either use activation here or not, right? So generally, let's say here we use the linear form. Right? So basically, it is just so basically just beta 1 0 plus beta 1 1 Z1 plus beta 1 2 Z2. Okay. So this will be the value of your Y1. Okay. So you're not actually applying any activation function. So for the last step, you can choose to apply activation function. That means if you choose to apply, then basically it will be, instead of this term, you will again apply you basically calculate the make a further calculation by using this linear input as linear input into this activation function. All right. So here we keep it simple, so we don't want to. So we only keep the activation function to the early layers here. The last layer we don't do anything, so we just take a linear form. So here will be beta 20 plus beta 21 z2 z1 plus beta 22 z2. Okay. So basically you have then you have a value for y1 and y2. All right. And then the last step is so the last step, you want to determine whether you want to fire. So this is what we call firing. Okay, 1 means firing, 0 means not firing. Okay, so the firing basically is just corresponding to a particular classification, right? So how do we do that? The one way to do it is to use a method called a function, actually. So use a function called softmax. Yeah. Okay. So in the last stage, you will apply a softmax. Right. So this will be, I use a G1 or okay. So let's say my Y1 node here, right? Okay. I will make a distinction here. Let's see. I will use this notation T1. Okay, so this will be my T1. And this will be my T2. Yeah. The Y1 and Y2 I want to reserve for 0, 1 kind of state. Okay. You can actually get your Y1 and Y2 from this function. Right. So I will just use T1 here. So this function, you can, when you apply something called a softmax, it's equal to the following. In this case, for binary case, you will basically just have, okay, you take the exponent and then you, so this will be the total, okay, and this is the contribution from T1, all right. So in general, if you have multiple nodes there, you basically will just have ET K over the sum of all the nodes, okay? This may be something else, okay? Right, so basically this will be the total and this will be the contribution from a particular, for a particular terminal node, all right? So this is the so-called the softmax output function, yeah? It's what we call an output function, the softmax output function. As you can see, this function will be constrained between 0 and 1, yeah, because of the fact that it's constructed using the total here, and this component is just one of the components. So it's constrained between 0 and 1, which gives it a probabilistic interpretation, yeah. So at the end over here, you can basically for a particular input, right? So let's say for a particular sample with certain values, yeah, this sample 1, sample 2, sample 3, x1, x2, x3, right? For particular values, you can have 2 columns here. Okay, so the first column will be the function gt1, the other will be g2t2. So let's say, for example, it may output 0.8, this may output 0.2, and so on, okay? So our prediction for the class will, of course, we will take the larger one, right? We take whichever one is larger, okay? So here, Therefore, we will predict my y1 to be 1 and my y2 will be 0. Okay. Right. So once you have the softmax output function, you can basically decide whether to fire or not. Right? Just take the one that's larger will be the firing state. Right. So in a nutshell, this is how a neural network actually operates. So here I maybe just do a simple calculation, right? Just to make things more concrete. So I'll make an illustration here, yeah, to show how the calculation actually works. So let's say you have 3 nodes here. And this is your X. This is your input layer, right? And let's say here you have the hidden layer. So denoted by Z. Right? Then here you have your node 1, 2. So this is the output layer. Okay, so these are your edges. Just using different colors. Okay. Okay, suppose we already, from the algorithm, right, later from estimation, we find out that we have the following values. Okay, for here the weight is 1. From here the weight is -1. And from the other side the weight is -2. Okay, suppose. And for here my weight is -1. This weight, let's say it's 1. Maybe I use 1. So this one is 1 and this one is -1. Okay. So these are the weights, right? And of course, the intercept will come from the node here. So let's say this will be okay, maybe the black one. Okay, so the value here, let's say I will use here I will put 2, and here I will put 1. Right? So basically the value on this edge is the intercept parameter value. Okay. So now let's make some calculations. Yeah. Okay. So for here, let's say I will use the rel_u activation function. Okay. So basically, max of 0. X. Okay. So here, let's compute the input value. Right? So what's the input value for this node? So I have basically the following. Okay. So suppose the observed value here is 1. This is 2. This is 1. Right? Okay. So these are your observed input values. Okay. So basically, to calculate the input value for node 1, before we put it to the ReLU activation function, it will be you take 1 times 1 here. Okay, the weight, yeah, give it the weight. Plus, so this the input is 2 times the weight here minus 1. Plus the input is 1 here times the weight minus 2. Okay, and then you'll finally add the intercept parameter. So that's, you add 2. Okay, so altogether this will be, so 2 and minus 2 will cancel. So you have minus 2 plus 1, so you have minus 1. Okay, and because this is minus 1, so when you do, you have ReLU of minus 1 is the same as max 0 minus 1, so you get a 0. Okay, so basically now your input value here, so the value for this node is 0. So let me use a different color. You have 0 here, right? Okay. And for this node, so we can do the same. So you have 1 times the weight is 1, plus 2 times the weight is 1, plus 1 times the weight minus 1, right? And then you add the intercept value, which is 1. So this becomes, so 1 and 1 will cancel. So here you get 3, right? So the ReLU function for 3 is basically 3, right? Because 3 is larger than 0. Okay, so you end up with the value 3 here. Okay, right, fine. Then we continue, right? So to continue, we have this one. Now the 2 sources, and then okay, the other 2 sources. Okay, so now let's say suppose we also know the parameter value here. So this is, let's say this is 1. Let's match the color, okay. So let's say this is 1, and this is 2. And let's say over here you have 1 and minus 1, right? So of course you'll have your bias. So let's say the bias is coming from here. Okay, so for this one and this one, okay. All right, so for, let's say, the intercept value for the purple, okay, for this set, yeah, the purple, let's say we put 1, and for this one we put minus 1, okay. Then finally so to calculate the value for T1 here, yeah, for the last node, so this node will be 1. Sorry, the input, start with the input 0 times 1 here, okay, the weight of the edge, plus the value here 3 times minus 1, okay. So this will give you minus, okay, you have to add one more term, right? The intercept. So add, the intercept is -1, yeah. So altogether you have -3 minus 1, you get -4. All right. Wait, am I doing it correctly? I think this is 2, right? Okay. This is a 2, yeah? Because the weight is 2 here, huh? 3 times 2, right? 3 times 2. So this is 0 times 1, okay? So this is the intercept -1. Okay, this is the correct one. So this should be 6 minus 1, 5. Okay. Then you'll have T2. Okay, so you have 0 times 1 plus, over here it is minus, this 3 times -1. Okay, then you add a 1 here, right? Plus 1. So you have -2. Okay, -2. All right. So then the finally when so you can decide on the output function, right? So your output function, okay, for this node, yeah. So will be G1 T1, right? So that will be e of power of 5 over e power of 5 plus e power of -2, using the softmax output function. And G2 will be, of course, this, okay? All right, so you'll get some value here. And of course, you pick the one that is larger, right? So basically, clearly here, this one is larger, right? So basically now your Y1 will be 1, your Y2 will be 0, okay? Y1 is 1 because it's larger, right? Okay, this is larger than 1 is larger than 2, right? So 1 is so Y1 has the final state of 1, okay, and Y2 has the final state of 0. All right, okay. So are you clear with how the calculations are done in this example? Okay. I think it should be quite straightforward. Yeah. I mean, like once the weights are given, so the first thing is you just basically find a linear. So the linear input, right? Just multiply the input with the weights, right? Then you get this linear input, and then you use it. And you use the linear input in the activation function, right? In this case, if you take the value, then you will get the value for this node, okay? And then basically you repeat the process, right? You basically repeat the process, except that once you get to the final layer here, over here you can choose not to apply the activation function, okay? So here you might just take a just to take the linear result, right? So again, it's the same. You have the weight. Okay, you multiply with the result here, and then you have your T1 values, right? And then finally, you further transform this using an output function. Okay, this case, use the softmax. And then after that, you compare which one is larger, and then the one that's larger will be output as the state 1, okay? 0 otherwise, right? So, in fact, the calculations are actually quite straightforward, except that, of course, since this network can be, the architecture can be quite, you may have many inputs, right? And you can also have a lot of input nodes. So it just looks complicated, but actually the principle of making the calculations is the same, yeah? It looks complicated because you're doing many transactions. I mean, you are kind of like doing many similar kinds of calculations like this, so it kind of like looks complicated, but actually it's the same kind of computation, right? It's just that a lot of them are taking place, okay? So in terms of the calculation, this should be quite straightforward, okay? All right, okay. So I think the calculation is okay. Now the question is, so how do we know these values? How are these values known, right? Okay, of course, when I give you these values, calculating this is basically easy. But in the first place, how do we know all these values? Yeah. So there has to be a way to estimate the parameters, right? So we need to actually estimate the edge parameters, right? In the ANN model, okay? So there are many, in fact, you can see very clearly that when your architecture becomes complicated, the number of parameters will increase dramatically, okay? In just now that example, right, where we basically only have one layer, so here, these are your input nodes, right, your X layer. So let's say I have this X layer. So let's say I have, so this is X, so X1, X2 until XP. Okay, P is the number of variables, right? And in the Z layer, okay, so I might actually have Z1, Z2 until Zn, okay? So M is the number of hidden number of nodes in the hidden layer, okay? So from here itself, right, you see one node, okay, connects to M nodes, right? So that's a factor of M. And since this node, right, you also will connect to the other nodes here, right? So altogether, there will be M times P plus 1. So over here, actually, it will be M, okay, it will be MP, right? Okay, M here times P, right? And then you have to add this another M terms here for the intercepts, right? Okay, so for one node here, you will basically have P coefficients, right? Plus 1 intercept, okay? So basically it's like P plus 1 times M, okay? And you factorize this, right? So at this layer, you already have M plus 1, N times P plus 1 parameters. Then from here, you go to the say K. So this will be your output layer. Right? So output layer, you have, let's say, K classes. Right? Your K, of course, has to be at least 2, right? So from here, again, the same thing, right? You have, you connect, okay? So basically you have, how many parameters have you got? So the same here, so you have M plus 1 times K, right? K is the number of nodes you have in the output layer. M plus 1 because you got M nodes here, and then the plus 1 is because of the intercept parameter. So how many altogether? How many parameters have you got? P plus 1 M plus M plus 1 K. This is the number of parameters. In this architecture, yeah, where you only have one hidden layer, all right, this is one of the simpler ANN. Of course, you can opt not to have the hidden layer. If you don't have the hidden layer, your neural network basically just becomes a multinomial logistic regression. Okay. So if no hidden layer, your ANN is basically just multinomial logistic regression, right? Because then at the end here, you basically just directly connect, right? Your X1 will directly connect to Y1, Y2, and all that. So then you have basically, if you apply a sigmoid function there, then you have a logistic regression. It's multinomial because you may have, in general, you may have more than 2 classes, okay? Right, okay. So the number of parameters will be equal to this. And let's say, suppose for binary case, right? Binary classification, K equals to 2. So you basically will have P plus 1, M plus 2, M plus 1. So if, yeah, so basically, can you simplify this further? So PM plus M plus 2M plus 2. So PM plus 3M plus 2. Okay. Right. So these are the number of parameters, and this will be generally equal to PM plus 3M if your PM are large. Okay. Okay, so you can see how many parameters you have, yeah? So especially if your data set is large, right? If your data set has a lot of variables, then your P is already high. So you may actually have so many parameters, right? And when you have a lot of parameters, your model may be may overfit very easily, yeah. So that's one of the problems. So you may actually have to do proper variable selection to control P, and also try to so this M should not also be too large, right? Of course, you need to strike some kind of balance, okay? Generally, if the number of nodes in the hidden layer is sufficient, then your ANN will perform well, right? Not too many, not too few. Because if you have too many, then it will overfit. If you have too few, then it may fit not that well, right? So the trick is to maybe try to find some kind of a balance, right? You may consider taking like M to be maybe half of the number of P, okay, or 1/3 or 1/4, right? Something, some rules like that. Okay, so generally these are the number of parameters, right, that you need to estimate. And how do we estimate that? So I'm just going to sketch out roughly how this is done. Yeah, well, we don't want to go to the technicalities. So basically, you need to define some kind of loss function. Okay. So for regression, you can actually use you can actually use AN for regression. So if you use it for regression, your loss function will be given by the following. So here I use theta to denote all the parameters. Denotes all the parameters. Okay. So this is actually a vector, yeah. Okay. Basically, this is just a squared loss. Very easy. Okay, so this is your I, this is your K. This is a squared loss. Okay, this is the predicted value. This is the observed. Okay, so then so this is a loss function, yeah. So because your function here, your alpha and beta parameters actually go inside here. Okay, so you can actually use a gradient method. Okay, gradient method, which means you have to take derivatives. Yeah, you have to take derivatives. Okay, you solve for z. Then you have to kind of like do something like this. Okay, and then you have equations. You get equations that relate to one another. Yeah, in terms of alpha and beta, right? And then you will solve numerically. Okay. Right. So there's actually an algorithm that actually will solve these equations numerically so that they will return the alpha beta parameters to you, right? For classification, they use the loss function is given by the following. Okay, so again, you also rely on taking derivatives, right? And then solving the, so you find some sets of equations here and then you solve numerically, right? This is the something called cross entropy. Okay, so generally this is, so we won't go into this part, yeah, because this part is very, it has a lot of those numerical computation things, so which will not concern us, yeah. Okay, but it's actually, you need to build a numerical solver like this to work with the neural network classifier, right? So that you can actually obtain your parameters, yeah. Okay, once the parameters are obtained, then deciding whether a node actually fires or not, it becomes simple, yeah. Okay, so this is the general approach used in a neural network, right? And a neural network is good for one thing, is so your ANN is good for prediction without interpretation. What does this mean? Okay, prediction without interpretation is a kind of classification work, right? Where you basically do not bother with explanations, right? As long as the classifier is doing well, you are happy. Okay. Like for example, identification of, there are some kind classes of problems where this is actually the view. Like for example, identification of zip codes, handwriting. Okay, so this generally people use ANN to do it because you basically just want to recognize what people are writing. So you don't really need to explain why this is, you don't really need to explain why this is classified as W, right? You don't need, similarly, you don't need an explanation why this is classified as a T. Okay, you just need for the classifier to tell you that, well, this is T, okay? So that when people write on the envelope, right? Let's say, clear this. So let's say just now that problem is very good for what we call if you scan the letters, yeah, if people say if people write something like this, okay. So once you scan this, right, it just needs to identify. Okay, there are some other things, right? So it needs to identify this handwriting as London. Okay, then it can actually sort this to, well, to be delivered to London, right? Instead of using a human being, so you can actually move the envelopes through some kind of a machine, right? Where it will, so the machine has there's a scanner here. It will scan this. It will obtain the machine. Sorry, it will obtain the image, right, of the letters here, and then this ANN will process it, and then it will recognize the characters, right? So you, for example, if you have these things, then basically it's a prediction problem, right? Where basically you are predicting 26 states for the 26 characters, yeah, A, B, C until Z, okay? So you see a character like this, you want to predict it as A, B, C, right? So it's a classification problem, right? So the ANN will finally predict, okay, from the image what this handwriting is about. So and then let's say, so it will, let's say over here the machine will record as London. So then it will maybe put it in one pile that's going to London, and this pile maybe going to somewhere else, maybe this part to Manchester or whatever, right? So basically sorting, right? So you don't need to use human beings, all right? You just need to have this machine, and somebody just pours the mail into the conveyor belt, and then so you have the hardware to basically feed the letters to some kind of production, some kind of pipeline, and then you have the software, right? The software is running on a classifier algorithm, okay, properly done, and then it will, from there it will control the pipeline some more, and then it will send the letter to the correct place, right? Okay, so this is one of the application where prediction without explanation is useful. Okay, but for other cases, usually people want to know why certain things are predicted in a certain way, right? So in this case, ANN may not, although it may perform well, but there may be some doubts on using it, right? So this is what we call a black box method. So ANN is called a black box, okay? But in general, it does quite well. You can always improve ANN by increasing the number of layers, increasing the number of nodes in the hidden layers, right? And your ANN is sure to improve. Okay, that's why those people who are very familiar with ANN, they basically don't care about other classifiers, especially the computer science people, right? What they only care is computation, yeah. So they have ANN, it's a black box, sure, but if all you care about is prediction, then they will just focus on tuning all the parameters so that their ANN is doing extremely well, right, compared to other models. Currently, when this ANN is used in the zip code problem, it's been found that, okay, so there are large, this is a classic, I just briefly mentioned it, right? So this is actually a classic example of ANN in zip code identification. So, so people have done, there's a database called NIST database. So collect with handwriting, yeah? Handwriting images. Right? So currently the database has 60,000 training set, very large, and 10,000 test set. Okay, also very large. Right. The current error rate is about the best error rate, about 0.8%. Okay, slightly less than 1%. Right. So so this is the current state of the art, okay, for handwriting recognition. Of course, if you write some scribble like this, okay, you scribble something like this, is very hard for the, maybe it will make out this as an M, right? Maybe this an A, but basically here, I don't know, it will maybe put a question mark, right? And maybe something else here. Okay, so maybe this is an L, who knows, right? So if the handwriting is really poor, right, of course your algorithm will also not do very well. Yeah. Okay. This is if you are interested, you can follow up this study. You can read a bit about this. It's basically done by a person called Lecan, right? Lecan. Maybe a French name. So for images, basically what they do is you might be curious how they work with images, right? So basically it's like this. So for images, it works like this. So you have to work with a square, right? This is a square, okay? So then you basically have, you partition the square to grids, yeah? So this is one way to partition it, for example. 1, 2, 3, 4, 5, 6, right? 6. You can do a 6 by 6, yeah? One, two, three, four, five, six. Okay. So if you have a letter, let's say F, right? So the F may be like this. So your F will be, if people write the F like properly, right? So it'll be something like maybe like this. Okay. So once you image, right? So basically this is like a matrix, right? So this is 6 times 1, 2, 3, 4, 5, 6. So 6 times 6, right? So the parts where it is almost blank, right? So you will have 1, 0. So this will be 0, 1, 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, maybe 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay, so you have a 6 by 6 matrix like this, right? Yeah. So, but then you can linearize this, right? You just convert this into a vector. So basically, this will be the first row. So you go like this. Okay. So you have 0, 1, 1, 1, 1, 0. Then here, you can have, wait, I mean, like you can read, you can just basically take this first row, put it here, take the second row, put it here, and so on, right? So you have 0, 1, 0, 0, 0, 0. Then the third row, 0, 1, 1, 1, 0, 0, and so on, right? Until the last one, 0, 1, 0, 0, 0, 0, okay? So basically, so this will be your variables, yeah? Okay, the variables on the, so this is your first variable, second variable, third variable, and altogether you have 36 variables. Okay, this is how you generate. So this image will have this data vector as this data vector, right, to represent it. Right? So of course, different patterns, handwriting, right, they will have different patterns of 0 and 1, right? But the ones that are actually closely related, so they will have data vectors that are kind of like similar. Of course, the 0, 1 here will change slightly depending on how the handwriting is done, right? Okay. So for example, some people, when they write F, they may actually just write until, let's say, maybe write until something like this. Then of course, this part will mainly be the same, but then there are some of these ones will change to 0. Okay. But then in principle, that should not affect how you classify your F, right? Because they are still more similar within them, among themselves than with other characters, right? So basically, this is how they generate this input vector, and if you put it into a neural network, right? So the first layer here, you already have how many nodes? You already have 36 nodes, yeah? Then you have to decide how many nodes come in here, right? So if you take maybe like one quarter of it, so there might be 9 nodes here in the hidden layer, right? So you have your architecture like this, okay? Okay, and then you have, in this case, you have 26 characters, right? So, so you will have 26, okay? So go like that, right? So the architecture will look like this. All right, and of course, if your resolution is high, okay, so if you increase your resolution of your image, then the grid size will increase, right? Let's say you can do 16 by 16, right? You just make it finer, okay? So your data will be finer. And then, of course, over here, your nodes will also be a lot more, right? Let's say 16 over 16, that will be 256 nodes, right? So you can see if you use ANN, then the number of parameters is definitely going to blow up quite quickly, okay, compared to other methods. Okay, all right, so this is all I want to talk about for the ANN theory up to now, all right? And let's take a break. And when we come back, then we'll talk more about, we'll look at a few implementations, right, of the ANN in the R package called neural net. Okay, then I'll show you the decision boundaries, how it looks like. Okay, so we are going to take a break now. Okay. So so install install a neural net and then call neural net, right? And so we're going to keep to the Wisconsin breast cancer data, right? So that we have some kind of comparison, okay? Okay, so again, so this is just basically standard. Now, over here in neural net, it only has the sigmoid activation function, or some very kind of like old school activation function, okay? So if you want to use the more modern activation function, actually it makes a difference, yeah? If the correct choice of activation function is one of the factors that causes your neural network to do better or worse, right? So one way is you define you can define your own function, right? So basically you define so it allows that, right? So the person who wrote this package, they understands this and allows you to define your own activation function, in fact. So here we define the soft plus and the switch function, right? So soft plus is basically defined as a function with an argument x, right? Just make sure you don't use this x for something else, right? Otherwise, I may get mixed up, yeah? Sometimes you may want to use some other index like k or something else. So anyway, you use x. So log of 1 plus exponent x, right? The switch is x divided by the sigmoid function. Basically, it's x multiplied by the sigmoid function, okay? Now, you cannot use the rel u here because it basically needs the, for this particular implementation, it requires the activation function to be differentiable, yeah? So it uses a kind of, it requires this differentiability of the activation function. Your rel u is actually not differentiable at the point of 0, yeah, because there is actually a sharp change, right? You remember the rel u, so the rel u is like this, right? Okay, so that is actually a sharp change at 0, okay? So basically it's not differentiable at 0. Not differentiable at 0, okay? Which means your d dx max of 0 and x does not exist, yeah, at 0, okay? When it is on this side, right, when your x is less than 0, the derivative, of course, is 0 because it's just a flat line. If okay, just a minute. Someone is trying to come in. Okay. So, okay, so over this side, your derivative is of course 1, right? But at this point, the derivative is 0. Okay, sorry, it does not exist because if you come from this side, if you still remember a bit of your calculus, right? In order for the derivative to exist at the point, if you approach it from the left-hand side, the derivative must be the same as you approach it from the right-hand side, right? Here you approach from the left, the derivative is 0. But you approach from the right, the derivative is 1, yeah? So it's not the same, right? So you don't actually have, yeah? So you can't use the rel u in this case. But the switch is switch is actually, so soft plus and switch are actually quite similar to rel u. So you're not losing out exactly, okay? Okay. Then after that, we have, then basically it's just defining your neural net, okay? Basically, so you have your model, diagnosis, and then using all the 2 variables. Hidden now, okay, hidden. So when I put 2, 1 here, it means I have 2 hidden layers. In the first hidden layer, I've got 2 nodes. And in the second hidden layer, I've got 1 node, right? So you can see, so later you can see its architecture, right? So here it's implicit that I actually have 2 hidden layers. If you want more hidden layers, you just basically increase the vector here, right? And then well, okay, so over here, DAT is your data. Then this is your activation function, right? So I use, for this one, I use soft plus, right? Linear output equals to false. So towards the end, so that means towards the end, when you have, let me annotate. Okay, so you have a neural network like this. So towards the end, so over this side, whether you, so you will still have some kind of a weight here, right? Beta 1. Maybe beta 1, 1, beta 1, 2, beta 1, 3, okay? So whether you basically, so then you basically have your Z values here, right? Z1, Z2, Z3. So basically you have Z1 B11 plus Z2 B12 plus Z3 B13. If you put linear dot output, that means you will take this value as this thing. Otherwise, it will go through another round of putting it through the activation function, right? So basically you can so by default I'll just put it at false, right? If you want to tune it to true and see what happens, it's also okay. Right? It's just to let you know there's no fixed way to do this part, right? Basically the last part people just leave it like kind of like linear. All right, okay. So all right. And then basically you can visualize your network, just plot, right? So it's actually quite straightforward, all right, using the function. And over this part, you basically do the sigmoid and the switch, right? So different models. Then you have your prediction results, okay? Use predict, and yeah, actually this one is wrong. This should be DAT, not iris. Not the iris data set. Okay, so you have this thing here, and so basically now this predict, in this case here, it will give you it will not actually give you your probability values. Okay, it will basically just give you the linear values, right? So unfortunately this predict function, right, depending on how the model was actually done, the kind of output that it gives at the end is not consistent from model to model, yeah? Okay, some models, they will actually give you the probabilities. Some will give you the class label, the predicted class labels. But in this case, this one, it only gives you the linear values, right? The one that you use the beta, with the beta as the coefficients, okay? So here, therefore, what I do is I basically do the softmax output, right? So I basically take the output, I exponentiate it, and then divide by the sum, right? So basically here, I do my own softmax, okay? So you can do the softmax for the other two activation functions, right? So over here, this part basically is I'm trying to, also once I've got the softmax, I basically try to find out which of the class, right? Which one has the largest probability, all right? And then I basically I predict the class, okay? Using the class with the highest probability, right? So basically this part does that. I mean like basically this part I use, I basically find out which one is the largest. And here basically it's just to convert it to the actual label. And here is the tabulation of the results, right? You have the contingency table, right? This is just to output the contingency table. And these are basically the same thing for the different activation function, okay? So here, so this decision boundary plot, right, is recycled from the previous one, but you have to run this. This is kind of like different because I changed some of the things inside, right? So apparently, it's because of the fact that the predict here, right? So you, in this case, it does not actually give the class label directly. So I have to go inside and kind of like make some tinkering before it will actually work. If you use the previous one, if you use the previous plot dot boundary and you put the model and data here, it will break, all right? Because of that peculiarity, okay? In fact, this was commented by the person who wrote this function, said unfortunately not very consistent between models, right? This is the part. Anyway, I kind of like I already hacked this part, so this will work properly, okay? And basically here, here you will just visualize, and we're just curious to see how the neural network decision boundary actually looks like, right? Even though the architecture kind of like looks a little bit complicated, but maybe the decision boundary is actually not so complicated, right? Okay, so let's try to run this. So I'm going to run this now. And then we'll see the output together, right? I'm going to share the console. Share the console. R console, okay. Can you see my R console?
Yes.
Oops. What are you seeing now?
SetWD, the set working directory desktop.
You are seeing my R console, yeah?
Yes.
Okay. Right. Okay, so I'm going to run the code one by one now. Okay, so I'm just going to. Okay, so I'm running it. It will take I think maybe a minute. Oh, okay, actually faster than that. Right, so that's done. How fast it actually runs will actually depend on how complex is your architecture. Okay, so now I have my. Let me share the. Okay, so can you see the diagram?
Yes.
Okay, so here you can see that, so your radius first and your concave point means, right? So these are your two variables, okay? And these are the edge weights, right? So you've got these two edge weights. Okay, and this is your coefficient. So this is your intercept coefficient, right? The so-called bias term, right? Okay, so now you know that this is your alpha 10, alpha 11, and this is alpha 12. Maybe I can annotate. Let me annotate. This is like your alpha 10. This is your alpha 11. This is your alpha 1. Sorry, alpha 12 should be this one. Okay, I just put a hat there to indicate it's an estimate, right? So over here, this will be alpha 20. This is your alpha 21, alpha 22. Okay, and then of course over here, this will be your beta 1, 1, beta 1, 2. Okay, so okay, let me see. This should be okay, right? So this is your beta 1. Okay. So again, so this is basically just this is another layer. So you might actually have another parameter here, like gamma, for example. Gamma 1, 1. It's gamma maybe. Actually, let me see. This should be 2, 1, 1, 2. Okay. 1, 2. No, this should be. This one indexes the. So this is 1. It's 2. Okay, so this is okay. Well, okay. Let me just get a hang on the subscripts. Yeah. This one, this one, this one. Okay, so one pair. So okay, that's one group. And then you have this one, this one, this one, right? So this is in. So this number is index for the node 2. Okay. So therefore this should actually be, so let's say this is 1, it's 2. So this is 1, this is 1, okay. Yeah, this is 1. So that should be 2, this will be 1. Okay. This indexes the edge. Okay. So this is 1, 1, this is 2, 1, right? So this will be, okay, so this is 1, 0. So this is used for both this and this. Okay. So this is so this should be 1, 1. So okay, this is 1, 2. Right. Right. So again, this one is parameter 1, 0. Okay. 2, 0. Okay. All right. So basically, yeah. I mean, here I just purposely put in an additional layer so that you can see how it actually looks like. Right? I just put 1 for simplicity. Okay. In fact, you can actually, if you want to just duplicate whatever I talk about now, just a simple theory with 1 layer, you can remove the C2 one. You can basically remove this one, right? Then you will actually just get this layer, right? And straight away goes here. Okay. So this is just to an illustration. So it's nice that it actually makes the diagram for you so that you can see what is going on. Yeah? So as you can see, so you also have this, so you have the weights here. And finally, you decide, right? So you have an output function. Okay, the output function we will do ourselves, right? Using the softmax. Okay. So now let's go back. Okay, so now I'm going to make the prediction. Okay, so these are the predicted values. So you can actually take a look. You can see the console, yeah? Right, are you seeing my console?
Yes.
Yeah, okay, so these are the predicted values. As you can see, they're actually not probabilities because they go out of 1 already, right? So this basically just it's just a linear output, okay, from the model. So because of that, we do the softmax. Okay, softmax. Basically, then you can take a look. Okay, so once you do the softmax, it becomes a probability, all right, and they sum to 1. So we can basically, like for example, in these two cases, we'll pick this one as to predict the class, right? So then we look at the labels. Okay, so this one, of course, this prediction is just based on your entire training set, right? But of course, if you want to use the test set, you can change here, yeah, for the predict. Basically, over here, you can change it to the test set, right? Okay, in this case, I just want to be simple, so I just use the training set as for prediction. So there, okay, you have it. Let me see. This one. Oh, I think the labels are switched. Actually, this is not BM. This should be MB, because otherwise it doesn't make sense. Okay, so I think this one is because I have to set it wrongly. I think should be maybe just like this. Okay, let's see. This table. Mm. Oh, okay. I have to redo it somewhere else. Okay, let me see. Um, Not here. Okay. Okay. Because I kind of like redefine my function, so I have to rerun it at this level. Okay. Okay. So basically, you change this. Just now I used the wrong. I should actually basically just define as B and M. So you can see basically just because of the labeling was swapped. Okay. So now you see that most of the predicted results are on the diagonals. Yeah. Okay. So otherwise, it would mean that this predictor is making kind of like opposite kind of mistakes. Okay, then so we are done with that. So it looks like it's doing quite a good job. All right, good job prediction. So let's run the plot boundary function. Let's plot the function. Okay, so let's take a look. Can you see the figure? Can you see the figure?
No.
Oh, okay. Right.
So Amy is waiting for your approval to get into the thing. Yeah.
I think she's in already. Is she? Let me see. Is she in already? Is Amy in already? Already.
Yes, she is in already.
Okay, fine. Okay, what happened? Okay, can you see the diagram?
Yes.
Yeah. Okay. So this is the predicted decision. So this is the decision boundary for your neural network, right? So it looks pretty much like your linear kernel for support vector machine. Okay, this one it looks almost like a straight line. Okay, so let's take a look at the other cases. Yeah. So I'm going to run the other models. All right, let's try to run the other models. We'll do the let's do the swish and the sigmoid. Okay. So it will take a bit of time. I don't know how fast is this. So the default is sigmoid, so you don't have to indicate anything, yeah. Oops, what's going on? Do I have switch? Hmm. Oh. Error. Okay. Strange. Say if I put 1. Okay. Well. Okay. Let's. Okay. It may be because of, I don't know, maybe this one has got something to do with, why does it return an error? Okay. Maybe certain architectures will not be allowed, I think. Because the data set actually you only have 2 variables. Yeah. Yeah. So, okay. So it has a convergence problem with, so it's giving a warning saying that maybe the parameter estimates, they may not be very reliable. Okay. It's the same with the sigmoid just now. Okay, but let's see if we can plot it. Generally, if you have you use the whole data set, then maybe okay. Yeah, okay. So this one it basically just says that your okay, you can't plot it because in the estimation part, the algorithm did not converge, right? So okay, so maybe for switch we can only use one layer and only one node, right? So that will work. Okay, so it works. So we have to use this. Let's look at the predicted results for switch. Okay. All right. So this is the result for switch. What was the result just now for soft plus? Let's take a look. Okay. So yeah, so switch is doing better with the benign, but soft plus is doing better with the malignant. Okay. Let's look at the boundary. Okay, so this is the boundary, yeah. All right, so this one is also very similar. Okay, it's a bit. Actually, it has some additional things here. So maybe the boundary is actually not just a straight line, but it's some coverage that goes like that, right? But we can't see the part there because I didn't plot it, okay? Right, so okay, so if you use switch, the decision boundary is something like this. So let's try to look at the sigmoid, right? So let's go back to the sigmoid case. Okay. Can you see the plot? Can you see the plot?
No,
No.
not at the moment. Yeah, cannot see.
Okay, now
Yes.
you can see the plot, right? Okay, so basically, yeah. So if you have only a single layer, 2 hidden nodes, so this is the architecture. Okay. Let's go back to the console. So we predict. Here's the result. And okay, so this one is the result for sigmoid, right? As you can see, there's actually some so these 3 methods, they have some slight variation in terms of what kind of mistakes that they commit. Yeah. So this is like so now you can see that choosing your activation function is something like kind of like playing with the kernel function, yeah, in SVM. So these are when you use this kind of classifiers. So you should know what sort of things can be tuned, right? So that you can adjust. You can find some kind of tuning parameter that makes the model do reasonably well, yeah, for your test data. So let's plot now. Right. So can you see the plot?
Yes.
Okay. So in this case also, yeah. So all 3 of the decision boundaries look kind of like linear, right? They only have very slight variation, yeah. So. Okay. So that's the demo, yeah. Okay. So later, if you want to play, all right, play with the code, then be sure to make some changes, right? Okay, so be sure to make the change to this part, okay? And you probably need to play with the architecture a little bit. Of course, you can feel free to actually do it on the entire data set, right? So, well, actually, why don't we try that, yeah? Okay. So let's try that, okay? So if you want to try it on the entire data set, then it would basically be just the following. So the format needs to be that our diagnosis needs to be at the last column, right? Because if you want to use the plot boundary, yeah, because the plot boundary assumes that the position of the class label is at the last column. So, but in our case, our breast cancer, I think it's in the first column. Yeah, it's in the first column. Sorry, the second column. So we will actually do something like this. We say that our DAT is without the first two columns, and then you have breast cancer, and then you append the diagnosis, right, on the to the last column. Okay, this should work. Oops. Oh, okay. No, sorry. Something like this. Data frame. Okay. The data frame consisting of this part appended with this column, right? So let's check. Okay. So, okay, then we kind of like, so the column name, we kind of like change it a bit. So column names, T, change it to diagnosis, right? Okay, so this should do. And then basically, then we just, so then basically we just, maybe we can do something like this. So run the soft plus again. Plot it. Okay, can you see the graph?
Yes.
Okay, so as you can see, since you have, so these are all the input nodes, right? Since we are using all of them, yeah, so basically you have an architecture like this, and so you have two hidden nodes here, two hidden nodes, right? So the architecture is like this, right? Of course, you can set some other values and look at what comes out, right? Okay, to continue, so okay, let's continue. Then we have prediction. Okay, so then we the tabulation. Hmm. Let me see if there's an error here. Result. Okay. In this case, everything is predicted as benign. So There's some anomalous things going on here. Okay, let's check. Oops. No. It's too big. Well, no, this will not work. Possibly, maybe, I'm not sure. If you use the whole data set, then some weird things come out. Possibly you might have to reduce the number of variables that go in, right? So let's see. Okay, we can actually take maybe just, let's say, maybe just a portion of it.
Will it be possible that it's not standardized, that's why the entire set is predicted towards to one end? I mean, the data is not normalized.
Oh, okay. You mean scaling, is it?
Yes.
Okay. So I wonder if there's a scaling. Do I have to do scaling on my own? Let me see if it actually has an internal scaling function. Let me just check. Okay, that is a reasonable possibility. Scaling. Doesn't have a scaling option in the model. Okay, we can try the scaling on our own. Does this work? Right. Okay. So scale, I think. Okay. Well, okay, so I'll just try this scaling function first. Scale by column. Okay. All right. So looks like it's been scaled. Okay. So let's do it again. Oops. Okay, there's some errors.
I think the soft class just now until right now, so we couldn't use whenever the hidden is equals to SQB, like 2 layers.
Yeah. Okay. I just forget about that first. So maybe I just use one layer. Not sure.
Or maybe we can use sigmoid if you want to.
It's okay. Well, anyway, I just want to see that it produces something, yeah. Because this kind of things, right? It depends on the person who wrote the program. So I'm not sure. Of course, I found this neural net by doing some search, but I'm not sure whether this is the best package to do neural network in R. Maybe there are better ones. Okay, so well, it's taking a bit of time when I specify the hidden, the number of nodes in the hidden layer as 5. Right, so maybe a few minutes. Didn't converge. Okay, interesting. So I just maybe put 2. Okay, so maybe I just do. Maybe we just try the sigmoid. Oh, sigmoid done so quickly. 3 hidden nodes. Okay. Okay. So let's look at the result for sigmoid. Okay. Okay, there you go. Almost everything predicted correctly. Of course, this is you have to realize that this one is you're using the training set as for training and prediction. But as you can see, when you use a lot of nodes, right? Neural networks tend to give pretty good results. Yeah. If explanation is not something that you need, okay. Even with in this case, there's only one. Just using one hidden layer with 3 nodes, you're doing quite well on the training set. Okay. So yeah. So I'm not sure about the other situations with the other architectures. It could be something related to the implementation, right? Somehow, but yeah. So we just well, it doesn't really bother us because there are all these possibility of different architectures, right? And some architectures may not run for reasons that are unknown to me, right? It might have something to do with the way because sometimes when you specify certain architecture and it just so happens that there are some, just because your data set has, when you specify under certain architectures, it has some singularities, right, during the estimation step. Okay, so certain things break in the estimation step, and therefore you get some errors, right? So unless you are the one writing it, okay, otherwise you don't know what the other person has coded and not sure what's going on. So basically, I think here the practical way to do it would be just to specify some reasonable architecture, simple ones, and then see what you get, right? Okay, so as you can see, this is like almost correctly predicted everything, right? But you should be always very suspicious of things that are predicting everything 100%, especially for complex phenomenon. Yeah, that always has the risk of overfitting. Okay. So this is all I want to talk about for neural network, right? And I know quite a few of you who are working, you might have come across using neural network yourself. And do you want to share your experience?
I don't use neural network in work because I'm working with a financial institution.
Yeah, they don't want that because it's a prediction without explanation. So they don't even want to look at it because you will be able to show some performance metrics that look fantastic, but trying to come up with explanation is a bit, although some people try, but still it's, well, there are some papers that actually claim that you can actually explain neural network results, but I think when I look at the architecture and I see that in between you can, because a lot of things like transformations, you have all this activation function that's actually taking it's taking a linear input and then mapping it to some space, right? That already introducing some kind of abstractness to the whole thing. So it will be really hard to explain the results, I mean, like, yeah, technically we can see that, okay, you're kind of like refining you are taking a linear input and you have your activation function that's non-linear, so it's taking it, so it's kind of like having some kind of you're doing like you're working with a linear combination, but then you have a non-linear rule to move it around in some space, right? So that you can do your prediction. So that would be, yes, I can understand that as you have a lot of flexibility in your model. Okay, and if your model is very flexible, then of course it will be able to classify things much better than, let's say, some inflexible model like just a straight line all the time, right? But the flexibility, how to explain that flexibility is a little bit still a bit opaque, I would say.
So I also did not use neural network in my work, but my boss did ask me to try some papers. One of them is to transform the time series into image and then try to fit into a CNN model. Yeah. But then the thing is, transforming the time series into image, there's a lot of transformation that you can transform time series into image one, right? And these are just like kind of they are trying to, this is just a way, and then there's nothing to be explainable on that kind of like transformation one. But then when you do this transformation, then people are ask how to interpret the transformed transformed image, which is not explainable. And then
probably you need to look into
they still despite they say, we want to try and end, but then when you do it, they will how to explain this, then they are like, and then it's not explainable ma. And then so cannot
that's what happens.
Cannot even pass the first stage of, after you transform the time series into the image, cannot even pass that one. And then why the image look like this? Can you explain the image? I mean, like how it is just like embedding or some kind of encoding the time series, right? So like that.
Yeah. So because it's you see, a lot of things are kind of like mixed up together, in your neural network, right? And each of them being given some kind of weight, and then you you have non-linear functions coming in and bring it into some other non-linear space. So yeah, it will be really tough to explain. I mean, like maybe if a few variables, maybe still possible, but if you start to have like 100, 200 variables, that's why it's more kind of like very popular for people who work with images. Because in images, basically you are dealing with the pixels, right? So the variables are pixels. There's nothing to explain about the pixels. Okay. Whereas in a real kind of data sets, like you have context, right? Each variable has a meaning, right? Because people spend time to collect certain variables, so they might have certain meaning, maybe in domain knowledge, whatever. So then it in terms of explanation, ANN will not do that well. But if it's working with this kind of you know, generic variables, like I mean, like this kind of variables that kind of like look more or less the same, like pixels, then yeah, then it has a lot of success. Okay, especially like this kind of computer vision things, right? Like you show a computer a picture and then it tells you what it is. These are all based on neural network, and I think yeah, because they know how to optimize it very well already. So the moment you go into this area, it's all then the best performing models are around this kind of class of model. But are there people here who have actually used it for work? So I know yeah, in some lines it's actually not so popular, right?
I think only for those that is working in the e-commerce or maybe this particular.
Actually, insurance did use like last time I checked with Jake about they try to identify the car damage using the image one.
Yeah, the
insurance
one that is not directly one is always usable, because if you have regulators come in, right, the thing's always gone hard by 10 times because you need to explain to them what is this and what is that. If there's regulators.
Oh.
Yeah.
That depends on the boss already. The CEO support this, so can do lah in my company.
See how well you can present it to the regulators until that they get your idea in general. Yeah. Did you ever look into the CNN explainer for the part of the explaining CNN? Because I think that's one of the good implementation according to some sort of competition last time that I forget which of them introduced this paper. I mean, this GitHub.
I think the CNN models, image kind of models, they already, a lot of pre-trained one is already very good. Everybody is just
you're applying the transfer learning, right?
Transfer learning, and then put in own label, and then you have to own self label all the car images. At least in my company, there's a department, there's two guys doing this. They try to label the car. They first do an object detection on the car, like this. Yeah. This from this photo, this car is. The first step is to identify the angle, okay. Like angle first. Like this is the front view, or this is the back view, or this is the side view of that car. Yeah. Then the second stage is to fit into a model, and then to take the parts. So like this is the bumper, this is the side door, and then this is the front engine part, and then the last step will be like how severely damaged it is for this part. And those cars who are like really not until like cannot recognize the shape already one, right? The model will have difficulty to find the parts, so because all the parts already gone, like the whole car front crash already. So that they are still working on it. I saw their accuracy, quite accurate actually. Only the like left and right is like not so accurate, like left door, right door, right? Because they are somewhat similar. Left or right
can
lamp.
Be inverted. Yes.
but they still get 80% accuracy already, even for those not like this. Then the bumper, all those at 90s, 97 accuracy is very good. So far I saw they doing this.
Are they allowed to implement into production? One curious question.
They're still in the process of doing. They're still in this second stage after they've labeled 1,000 photo, you know, manually label, and then they hire an intern to label 500.
So that intern spent 3 months to label it.
Yeah. They label.
Oh my god.
500. You know, the labeling is like you need to highlight this part is the bumper, this part is the lamp. One picture, one photo by one photo. Even the modeler himself also have to label himself. So it's like, okay, I salute them. MCO can do lah.
Then I have a ex-colleague that is doing the palm tree labeling part. He also because his task is to count how many fruits are there and then how many fruit is good and how many fruit is bad. So you can imagine one entire bunch is got how many fruits, right? He forced to label it one by one. Even though he got a lot of photos, but he doesn't manage to label it all because it's you need to draw the shape to let them know this is 1, this is 2, this is 3, and so on.
That's interesting. Yeah.
But I saw the most usage is generally either marketing or e-commerce because marketing wise, I think recently I saw some sort of startup they are doing this labeling kind of stuff. It's they went to the store and then based on the photo that they took, because it's just a front image, right? You cannot observe how many is left in the behind. So they pay some people, they find some online people to actually label it from there, and then they pay an amount of sum. After that, they do some sort of image recognition, how many stocks are there left, and what is this and what is that, something like that. It's going on. I just saw it.
So
I just saw it.
Where?
I don't remember the company name.
Okay.
Yeah. And then e-commerce wise, it's always more to, there are a lot of different things like machine translation. Since we are in Malaysia, right? So there are different kind of names for the items, for the same items. So they're trying to apply some unsupervised learning on the part of machine translation.
Unsupervised learning, how do they?
Yes.
How can they verify? Even if it's the same item in English, you put in Lazada or Shopee or a different name also. How they match it all?
That's why, because it's hard to label, right? So the main point here is in general, that's what they say. For every language, right? So let's say I'm saying this part I, me, he, she, something like that. So they will compute some sort of distance metrics to measure between that. So those distance metric, when it's about similar, is always in the same group. So when it comes to something like moving, shifting, and so on, then it will become having different length and also different distance metrics as well. So they do it for one language and for the second language as well. Then they're trying to rotate this particular so-called distance metric, some sort of coefficient to try to match to it. This is one of the ideas that they are doing for unsupervised learning. The other one is always definitely is image classification, because they want to have some labels, and also due to the data that they have is quite a lot of different class, right? 100 class, 200 class. So definitely they're having this data imbalance problem as well. So they are trying to solve this issue too. This one is from Shopee. Yep. Yeah, competition itself, they launched quite some number of papers for you to read.
Okay. Yeah, thanks for sharing your experience. I think that is actually helpful to others who are maybe just in the academic environment and maybe interested to know how people outside in the business and industry actually make use of these methods. Okay. Okay, I think we are just about on time. Okay, so that's all for today's lecture. I will update the R code just to clean up a bit of things, and then you can try it later. Yeah. Okay. So I'll repost the R code for the neural network. Okay, so that when you run it, you don't have all these errors. All right, okay. So I'm going to stop the recording now.
Thank you, Dr. Kang.